Yeah. So if you want to challenge my grading, of course we'll do that after class, or we'll do it in office hours. Okay. So I was surprised about several of your answers that you didn't get it right, because I thought they were pretty simple. But so it must be like the way the exam worked rather than the difficulty of the exam, in some cases at least. So first one here, let's see. So let's just go through the setting a little bit. So we have an office in Chicago, we have an office in New York. In New York, there's no office in New York, there's this stock market in New York. And we have a server over in New York, right, at NASDAQ. And that one can instruct, it can place orders on the market for us. So the advantage of having that server is that we can change stuff around, right? We can use different protocols internally for the company. Okay, they are 1,000 kilometers apart, and the ping utility says it's 25 milliseconds round trip time between Chicago and New York. Okay, so now we want to establish a new HTTP session for every trade. How long does it take before the Chicago program decides, between when the Chicago program decides to make a trade and the company server receives that order? Okay, so how does that work? Probably should draw this. Let's see. Where are we? This is not it. Fine, we'll make it more. So HTTP, right? It depends on TCP. So we start over here, Chicago, and here's our server. So now we first have our session establishment. I think everyone got that, or almost everyone. Not quite everyone. So there's a SYN packet, there's an ACK packet, SYN, and this one happens to be called the SYN ACK because there's both, and then there was an ACK. Okay, so this was not that uncommon for people to know. And then finally there's data, like the actual request. We'll call it request. Right, so that's the general setup with TCP. Now, how long does it take before the server in New York gets this information? First, we have a SYN-ACK. That's one round trip, 25 milliseconds, right? And then there's an ACK, and then there's a request. Here's Hardy. Okay. Here you are. Okay. So we have at least 25 milliseconds, but then we got to get this ACK over and the request over. Now, I saw lots of people saying, okay, that's going to take another round trip time. It's half a round trip for that and half a round trip for this. That's not how delay works. Right? These two don't depend on each other. Well, you got to send the ACK first, but we're not going to get an ACK on the ACK. We don't know when the server is getting anything. We just send the ACK. And then we send our request. So they're sent back to back with no delay between these two. So it becomes 37.5 milliseconds, right? 1.5 round trip. Okay? Questions on that? I think a bunch of people tripped up on the round trip versus one way, but it was also very common to be confused about what's going on here.
So how much time did it take for the ACK and the request?
So every arrow here is a half round trip, right? And the round trip was 25, so it's 12.5. So it's 12.5 there, 12.5 there, and then these two, they're actually going together, right? Because there's nothing that the request can wait for the ACK. So they're going together, so that's another 12.5. Okay. So now we have our brilliant CEO, and he decides that we need to bump up the speed here. We can make a lot more money if this goes faster, so let's spend more money and then make more money. We're going from 10 megabits to 100 megabits. So should that make things 10 times faster? A bunch of people thought so. Now, unfortunately, these orders are small. You can kind of tell from up here, even if it wasn't obvious, you can kind of tell from up here that this is going to be a small packet. It's not like we're sending megabytes and megabytes. So the actual transmission does not take 12.5 milliseconds. It takes not even a millisecond, maybe a few microseconds. It's a very short transmission here. Actually, let's see, on a 10 megabit, oh, it might take a millisecond to transmit it. I don't know. Something like that.
I'm not following you.
What's that?
Can you explain what you're talking about?
Yeah, so the transmission, here, we go back here. The transmission of this request is not going to take a whole lot of time. What takes time is you start transmitting it, right? And then you're done transmitting it, and then the request has to travel all the way to New York.
Okay.
So there's a difference between the bandwidth and the latency that I've been harping on for a while. And we have that here as well. So now we can actually send our message 10 times faster, but sadly, it almost took no time to send it in the first place out from the office, but then it has to go all the way up, to New York, and that takes just as long. You could imagine somehow that, oh, when you get a 100 megabit, everything is somehow different. Right? Oh, if I buy 100 megabit, then we're going to get a direct link straight to New York. But is this a regular internet connection we're getting here? Standard internet connection. So there's nothing special about it, except we have a faster link to our ISP. So how much shorter will the delay be after the upgrade? Almost nothing. Right. So if you said nothing, that's fine. If you said virtually nothing, that's fine. Anything else is probably wrong. Okay, so then we have a clever other colleague. They don't like HTTP. If you look at the HTTP protocol, you run TCP dump, you see there's lots of headers, all this junk, right? It's very wasteful. So now your clever colleague here decides, why don't we just use TCP directly, and we send a short, smart message here. Just exactly what we need to transmit. We can do that, and it becomes 1/10 the size of the original request. So now maybe the original request was, say, a kilobyte, in which case the transmission would have taken a tenth of a millisecond. So now we reduce it to 100 bytes. So now it's going to take 100th of a millisecond to send the message. That's great. 10 times faster to transmit it, but still, the message still has to travel all the way to New York. Right? We got it out the pipe fast, or out the door fast, but then it's taking a long time, so now it doesn't actually improve either. Marginal improvement. Then we have a guy with a big beard. He figures, why are we setting up all these TCP connections? Let's just have a single TCP connection, and we transmit all our requests on that. Right? So now you have a connection already, and we send a request. How long is it going to take? Well, let's go back here. This is the original situation, right? Actually, let's go like this. So that's the original situation. Of course, there's going to be an ACK as well. But the ACK doesn't really matter, because the server knows that it got the request already. It can place the order here. It doesn't have to wait until the sender got the ACK back. It doesn't even know when the sender got the ACK back. There's no way to tell. Okay, so in the new situation, the bearded dude's solution, we make more requests on the same link, on the same TCP connection. So now, how long does it take? And it says somewhere that we don't have very many, these orders, they don't come very quickly. And they come every now and then. I can't see it here, it says somewhere. So it's not like they're back-to-back, like constant orders coming in here. Okay, so under that assumption here that there's enough time for the ACK to make it back before we want to send another request. Now, how long is it going to take? Well, all we have is this arrow here. We don't need to worry about the SYNAC. We just have one arrow, so that's 12.5 milliseconds. Of course, if you do happen to have backed up orders, then things get different. Right? So if you want to go like this, now you might have a problem, because sometimes this ACK or the request is lost, you have to retransmit, there's a lot of delay, and now this request here is going to be delayed. So if there was really a lot of orders, then things would be different. Questions on this? Okay. Moving on. So this seems like a much better solution here. So now it's 12.5 milliseconds. But then, since we've done some UDP, we decide to try a UDP solution instead. So here we're basically sending the same message. It's the same short TCP message, but we're sending in a UDP datagram instead, which means there are no ACKs, which means there can't be any retransmissions. Okay, but so how much shorter is the delay if we're using UDP? Well, with TCP there was a 12.5 milliseconds, right? It's one arrow. And all of that, or virtually all of that, is because of the travel time between Chicago and New York. UDP packet still has to travel the same distance, so it doesn't make any difference. It's really not any better. Or if it is a little better, it's marginally better. This again under the assumption that you don't have back-to-back packets in your TCP connection so that they all start queuing up and all these things. Okay, but then there's the drawback here that if we use UDP, the packets sometimes get lost. And so they just never get delivered to the server. This was kind of a tricky question, I suppose. Because what we want here is, why might it be a good thing for this application to lose packets? This doesn't seem like it can ever be a good thing, right? You want your packets to be delivered. But in this case, if a trade order shows up late, it's probably going to lose you money, right? The whole point of this high-frequency trading is you want to get in there first. If you're getting in there after all the other people doing it, well, probably you're going to be the patsy. Right? So here the idea is, if the packet got lost, well, a TCP packet would also have gotten lost. Right? Packets get lost sometimes. These things happen. But what TCP would do is wait for a little bit, see that there wasn't an ACK, and then transmit again. So now we would send the order in much later, and that would be probably a dummy order, right? And you would be losing money. With UDP, yeah, we don't get to place the order. So we didn't make that money that we could have made, but we also didn't lose any money because we didn't place a late order. So it's a good thing because these packets are worthless when they arrive late. Yeah.
Would you give points for an answer that says stock market crash at the time after we should the order to buy?
Yeah.
Would you give the point?
I don't remember what I decided to do. So in general, so that I think that is an argument saying, it's not an argument. It's saying one situation in which it would be good. Right? But here the question is like, why is it good in general to be losing packets? For this application, most applications it's not good. But it is true also for things like, anyone? Where else is it good to be losing our packets?
Games.
Games? Yeah, probably. If you're shooting someone, it's probably better that you don't shoot late than that you. Well, so losing the shot is basically you missed, right? It's not so bad. Having it show up late and everything else be delayed after you, that's probably a big problem. So.
Voice over IP.
What's that? Voice over IP, yeah. Live video, any streaming live video. Anything where the packets are useless if they come late. Then we just want to throw them away. We don't want them to affect any other packets or to use any more bandwidth. Okay, we have a very expensive consultant here. Depends on how you count. Right? They can get more expensive than this too. He decides, let's just run the decision making at NASDAQ. Okay, so now there's no delay. Awesome, this guy is smart, right? So what, does it get much better then? Jake says no. A lot of people said yes. So the problem here is the time between when something happens to the beryllium price and when your company places their NASDAQ order. Okay, so the beryllium price here happens on the Chicago market. So if you are this decision maker, you actually have to know that the beryllium price changed before you can make a decision. It doesn't matter where you are. If you're in New York, someone has to tell you about the price. How long does it take for that information to come across? 12.5 milliseconds. Doesn't make any difference. So wherever you put your decision is probably you're going to have the same delay. And if you think,
Won't it be even longer because you have to ping Chicago and wait for the price to change?
Oh no, you could imagine having the Chicago office stream all of the prices over to the New York server. You can imagine even a special service, like something really clever that's only designed to stream resource prices over to NASDAQ, and it probably exists. But it's still going to have similar latencies. Just in general, it's not possible to go any faster than the speed of light, no matter what it is. No matter what information we're trying to get across. At least so far, no one's figured out how to go any faster. I sure hope they will at some point. Okay. So that didn't help. But apparently they're still making a lot of money. So CEO decides to buy a geostationary satellite. Okay, so to get this right, to actually get the numbers right, you'd have to know the orbit of a geostationary satellite. You have to be able to estimate the distance from here to the equator, and maybe. So that's really hard. But so therefore, you are not asked to say how, by numbers, how much. But let's think about what's going on here with our geostationary satellites. Does anyone care to make a guess how far out they are?
All satellites are the furthest.
Of all satellites, they are the furthest. No. The moon is further.
Wow. Halfway between the moon?
What's that?
Halfway between
Halfway between the moon and Earth? No, that's not the case either, but it's probably closer. 17,000 miles. That's not a half bad guess. Anyone else? That's not what's going on. First of all, the space station is not in geostationary orbit. If you look at it, it's just going by. It's going by around 20 times a day or something. It's at about 100 miles up. Geostationary satellites are much further, but it's okay. So I just want to do this one anyway. I like this stuff. So okay, so here's the Earth. We're up here somewhere. All right, let me put a little box for Chicago. And then we have New York. Where's that going to be? Like that, maybe. Right? They're not very far apart. 1,000 kilometers. How far is it? All the way around the Earth? 40,000. Yeah, exactly. So, if you want to be a geostationary satellite, you can't really choose where you are. We don't know how far up, because that's too hard to remember. It's actually about two circumferences. One circumference out. 35,000 kilometers, I think, more exact. But if you think of it as about one circumference, just string it out. Imagine you have a string around the globe and just kind of string it out. That's how far out it is. It's pretty damn far. But that doesn't matter, though, in order to get the right answer here. If you want to be a geostationary satellite, you only have one choice of orbit. You have to be around the equator. And the whole point is you're always in the same spot. Someone's pointing at you, you're always in the same spot. There's only one way to do that. You have to be around the equator, and you actually happen to be about here somewhere.
I wonder if you have to rent space. There's a finite amount of them.
Well, it's a very long circle. Right? This is 35,000 kilometers out, and by pi, then 2 pi actually. Yeah. And the satellites are not, they don't have to be. Yeah, you can fit a lot of them. Anyway, so it's maybe out here, it's a little further out probably. But even if we didn't know that they're in space, we just say, okay, they're on the surface, they have to be on the equator. Alright? So, okay, closest point on the equator is going to be over here. How far is it to the equator?
Further than short line distance.
What's that?
The equator bends definitely further than the direct distance.
Yeah, going to the equator, from here to the equator and then to New York, that's a lot longer than going straight to New York. We can agree on this. So that's all you need to know. Right. Now, if you then want to go all the way out here and then back to New York, you're in real trouble. So this CEO, he didn't really know what he was talking about. Okay. Any more questions on that one? So the main point here is satellites are far away. All right. Now, maybe you've heard of this Iridium. They're these satellite phones. Look like just big bulky phones. They have coverage all over the world. Awesome. They're very, very expensive to use, unfortunately. So how does that work? Because on a phone, you want to have less than 250 milliseconds or 200 milliseconds of round trip time, or people get really annoyed. So going out here, 40,000 kilometers away, that's more. And then you got to go back. It's 80,000 kilometers. Now we're talking, yeah.
Are there satellites that are closer? There?
Yeah. So what Iridium does is they put them, just like the space station, just almost touching the surface. And then they have lots of them, and they all go around and around like crazy, because that's the only thing you can do then. Yeah, you can think of it as a kind of constellation. Of course, they're never actually together. They're all going like around like that. So they have to have, 50 satellites or something all. Because when they're so close, they can't see the whole Earth. Here, you can see a lot of it. Anyway, so one more thing about this. Maybe, if you look at satellite dishes, maybe you notice that they're always pointing south. They're pointing up to some degree. They're always pointing south. Ish. That's why. Same thing with if you're on the south end of on the southern hemisphere. Well, then they're always pointing north, because they're always these geostationary satellites. They're always on the equator. That's it, way up. So if you're on the equator, where do you point your satellite dish? Straight up. Yeah. Of course, it can actually be like that too, right? Because they can be anywhere along the circle. So it can be depending on which satellite you want. Okay. That's a bit of an aside. So then the owner. I mean, a geostationary satellite is expensive, but digging a trench all the way to New York, that's worse. So how long would it be if you just put a tunnel, you dig a tunnel under all the roads, under all the subways, everything, you dig it straight to New York? Well, now we have to figure out what is the shortest possible distance. That's why we're making a tunnel, so we can go straight line. The shortest possible distance, as already stated, it's 1,000 kilometers away to New York. So how long is it going to take? Take 1,000 divided by the speed of light. You don't take the speed of light and divide it by 1,000. Like 5 people had that one wrong. So that gives you 1,000 divided by 300,000. All right. So what is that? 1 divided by 300, 3.3 milliseconds. So one way. So we can go down to 3.3 milliseconds. Actually, there are companies that do this. They don't dig tunnels because that's way too expensive, but they put microwave relays. So I think Goldman Sachs wanted to put a shitload of money into some ridiculous antennas so they can get this to go faster.
They did do it.
They actually did it.
That did it, and a couple companies were late, and theirs were completely useless. Basically, nuts. Just because you can't go completely straight underground, microwaves can go direct straight. It's crazy. So insane.
So here's the final. This was, of course, just a rhetorical question here, but it's sort of a pet peeve of mine here. It's completely pointless. This whole exercise is completely pointless. Maybe not for the people who are at the moment making money, but as soon as someone else digs another tunnel, right, wastes another few $1 billion, $1 trillion to dig another tunnel to get it a little shorter, then they start losing money. no one actually, there's no positive gain anywhere. So some people say the rich get richer. Well, the rich get equally richer as the poor get poorer in this case. Or maybe the less rich get less rich. Right? It's completely pointless. What ought to be in there is a turn-based system, so it doesn't matter. Every second everyone makes a trade. Forget about the rest. A second, everyone on the entire globe can get to the market in a second. So just do it once per second and it's over. But it's never going to happen. Okay. So this program here is actually pretty much the same thing. It's all about latency and throughput, just like the previous one. So here we have a program that sequentially takes one request and then figures out where is the data that I need for this nose-picking statistics. And that's actually instantaneous. Very, very fast. So we don't care about that. And then we go and find it on the disk, and then we compute something. Like how many times did they actually get something from their attempt to pick their nose?
Oh.
So, surprisingly many did not get this. And so I think that's sort of what screwed up this exam. That this one didn't get the right answer to this one. I put it there because I thought, okay, let's put a nice big honking hint here so that we don't screw up the rest. But it wasn't big enough. So how many of these short little requests can the system handle per second? So what is the limiting factor for this program here? Well, there's two actually. One is it's sequential. Right? We're just handling one request, waiting for the disk, doing a computation, sending off the answer, then we're doing the next request. So it could be helpful to be able to do them in parallel. And that's a couple of the parts down here. But what is the real limiting factor here?
The hard drive.
The hard drive, yeah. I put in a picture here of the hard drive and the SSD to give some extra hints here.
I didn't understand the fine offset. I just got it now. I don't have, because the reason I was so thrown off by this was that I thought, oh, I have to search the entire.
Oh, you didn't see this?
Well, I saw it, but I didn't really understand.
Okay.
I just didn't understand.
I thought I had to search the whole.
Ask if you don't understand the question,
Well, I did,
please.
but then I still didn't understand. I was like, oh, maybe it just.
Okay, so anyway, the limitation here is this arm, right, and the spinning of the disk. So how long does it take before you can get something on average? You want some random place on the disk. You want 5 to 15 as a fine estimate. I think Shyam said 7, which was an even better estimate. No? That wasn't you? It was someone else. Okay, good. Yeah, okay. 5 to 15 milliseconds would be perfect. So in that case, say it takes 10. Because 10 is such an easy number, and we want all rough calculations anyway. Take 10 here. So how many, if it takes 10 milliseconds to get, where is it? Here. This one. It's going to take 10 milliseconds. Right? We want to find something random on the disk. The seek here doesn't actually tell the disk to do anything. It just tells the operating system, okay, this is what I'm going to be interested in reading. But then read, has to go and fetch it. It'll take us 10 milliseconds. And then, depending on how big this is, it might take some extra time. But this is a really small query. These 5-minute handshakes ones, they're just, a few hundred bytes maybe, if it's some really ambitious nose picker here. Okay, so it takes 10 milliseconds. How many can we handle per second? And believe me or not, I don't know what the expression is, a bunch of people knew that it's 10 milliseconds and got the number wrong. Here we go. We have an example of this individual.
I didn't answer. I'm not trying to get it.
It takes 10 milliseconds. It's 10 milliseconds to do one of these. How many can we do per second? 100. There we go. Okay. 1,000 divided by 100 by 10. Yeah. But there were so many of those missing an order of magnitude things in these exams. So We got to get that straight. Maybe we should stop this whole systems thing and just do a little bit of arithmetic.
I studied that. I still struggle with it.
Yeah.
They have us doing all this calculus and stuff.
Should we
Just
start?
basic arithmetic.
We'll start with the number 3 table. 3 times 4 is...
Hold on.
Anyway. Okay, so here's a different kind of query. This is a lifetime yield query. So now you're asked, and this one is a actual little bit of calculation. You're asked to compute how large is one of these queries. Right? So for an ambitious frequent picker here, he tries to pick his nose once per minute. It doesn't say if it's at night as well. Okay? And then we want to get his entire lifetime here. So how big is that? Now, of course, not every picker is going to be 1 per minute. Like, this is a very rough estimate already. So we can screw around with the numbers a little bit. Let's try that. So we can say there's 60 per second. Right? But let's make it 50, because that's a much easier number to deal with. There's 20 hours per day, let's say. Say there's, 400. I kind of make up for the... So now I had too few hours, too few minutes. Right? So I'll make up for it by having a few more days in the year. Right? Okay. And then what? How many years are we going to do? 50 years, perhaps. So how big is this? That's 1,000 times to 20,000. All right. So that's 20 million. 20 million entries, and then every entry is 4 bytes, but let's call it 5 just so it doesn't get so hard. So it's 100 megabytes, right? We need 100 megabytes to compute this query.
Wait, where did the 5 come from?
Well, every entry is 4 bytes long,
Oh, okay.
but I figured whatever. It's nice to have 100. Yeah, so actually, let's try this. I want to try this with, yeah, I have an internet connection, so I just want to see how big is the actual number. 60 times 24 times 365, times 50. Oh, and times 4. We're pretty close. Within 5%. Right? So that's not going to matter. You don't have to do the careful calculations there. And that's sort of the point sometimes here. Okay, so we need 100 megabytes. How long is it going to take for us to execute this query? Well, our disk can handle 100 megabytes per second. Can give us 100 megabytes per second. And this is all single query sort of thing here. So we need 100 megabytes. Okay, it'll take at least 1 second to get it from the disk. And here we're reading everything in to the buffer, and then computing the yield. How long does it take to compute the yield? 100 megabytes? Not much, right? We have a gigahertz processor. Forget it. All these numbers are so rough anyway. Second, right? The disk is really dominating here. Read time on the disk is what really matters. So it takes us 1 second to do a single query. That's crazy. Okay, so we want to speed things up. Our manager again decides to pile more money on it. It didn't make things any better on the short queries. Why? Because we're limited by the latency of the disk. Right? We didn't even change the disks here, except we moved them to the new machine. So it's still going to take us 10 milliseconds to get some random data. What about the large thing? Now we're getting 100 megabytes. It'll take the same amount of time because the disks have the same speed. But then it got a little faster anyway. That's the yield. We actually have to do some computation here. It's 100 megabytes of data. We have to crunch through it. Things got a little bit faster because we went from a 1 gigahertz processor to a 3 gigahertz processor. It wasn't important though. So we return this extremely expensive machine. A machine with 100 3 gigahertz cores, that's going to cost you like $500,000 maybe. So, okay. So we, of course, are systems engineers, so we figure we'll just make it much better without the extra hardware. We use fork. So now we're forking the process right after we get the request here. So now it's going to go around. I mean, obviously we have a if condition and all that, so it goes around and it's right back here to trying to receive the next request almost immediately. And a forked process is doing all this work. So, is that going to be any better? Well, if we're lightly loaded, server's lightly loaded, there isn't much coming in. Doesn't matter. Right? Okay, we're doing it in a fork. Some other process is waiting for an incoming request, but nothing's coming. Doesn't make it any better. Okay, that didn't help. But then when we get a lot of requests coming in, now things change. Because now I'm handling one request, next request comes in, and a new fork is coming in handling that, and so on, right? Any number of forks here. So that ought to get better. Or, why could it get better? If this,
we still have to wait for the disk, and the disk can only read from one spot.
yes. So these disks are limited. They have one arm. They can read in one spot only. So is it going to get any faster? I mean, the CPU, okay, it's actually not that busy anyway. So that's fine. We can fork if we want. But the disks are limiting us here. So how can it get faster?
Wait, did you say there's 10
was
There's 10 disks. So every disk here can do something for us. Sometimes you get 2 requests in that deal with the same disk. Okay, that's going to get delayed. Next request that comes in is from another disk that isn't busy. So now we're reading from 10 different disks in parallel. We can do 10 times as much work. So how many more requests I said, but it doesn't really matter as long as you answer correctly here. So how many more requests can we handle per second on average with our clever fork here? Should be, we were able to handle 100, right? And now we're able to handle 10 times that. So how many more? It's actually 900 more, right? But if you said 1,000 requests per second, yeah, 1,000 requests per second, that's fine. Okay, so these are for the pre-handshake requests. These are very short sort of things. Some other guy comes in and says, okay, I'll just do it with select. Forget your forks. So why does that? Turns out it works the same. It works the same because the parallelism that's going on here is on the disks. It's not on the CPU. CPU is just sitting there waiting anyway. So we can do it any way we want. With select, select will tell us when the disk is ready to read from again. Right? And in the meantime, we're dealing with other queries. Okay. So finally, this is probably the hardest one in the whole exam. Switch out read with an mmap. So what does mmap do? Right? It sets up these page tables so that whatever's in the file appears like it's in memory. And then whenever I start reading from it, reading from that part in memory, it'll fetch that from disk. So it actually has to fetch everything from disk, just like read. Read reads in everything in one go. Look at the code. Right? In one go, it gets everything here. Whereas mmap, well, it makes it look like everything is there, but it's only going to really get it for you when you need it. So this all depends on how mmap is implemented, actually. It's not always going to be faster. If you have a dumb mmap implementation, it'll be slower. But here it got faster. Right? So why did it get faster? Well, with read, we have to wait for the disk to be done with the entire query, right? To read in the 100 megabytes. And then we do our computation. With mmap, we're doing the computation, and as we do the computation, the disk fetches the stuff we want. So now basically when we're done reading, we're also done computing. So we don't need to do that extra computation phase at the end. So it got a little bit better because we could forget we have more parallelism here. We're doing computation in parallel with the disk reading as well. For the short ones, it doesn't matter because the computation is so short, it just goes away. Okay, we're wrapping up almost. So now we take the select, the fork solution and the select solution, we put it on this monster server again. So now the monster server has 100 cores, right? And select isn't able to use those 100 cores. Fork is. So how much better are we going to do? We have one bid for 100 times better. And one for no better. So it's clearly going to be one of those two answers. Right? I'm not going to ask you to come up with like 46%. It's no better because the CPU isn't busy anyway.
Yeah.
We're waiting for the disks. Okay, so he got fired. And now it's all up to us. But we're going to get 10 times as many requests as we used to. So now we need to bump up the speed here. We buy a lot of disks. Right? Because the seek time on these disks is limiting us. 10 milliseconds per seek. For every request, we need to spend 10 milliseconds. So now we have 10,000 requests. We're going to have to spend 100,000 head seeks, I suppose. Right? Right? 100,000 head milliseconds. Head 10 milliseconds. Yeah, head milliseconds. That's what it is, the unit. Head milliseconds. So we need we need more disks. If we have 1,000 disks, 100,000 head milliseconds divided by 1,000 disks, that's only 100 head milliseconds. Does that work out? What am I talking about? Let's do it some other way. So with our 10 disks, we were able to handle 1,000 requests per second, right? Due to the parallelism. So now we need 10,000. Well, we need to have 10 times as many disks because everything was disk limited. So 100 disks. Now the other option is to buy SSDs, but they're really expensive. So, and they're actually not that much faster. In this case, they're exactly the same, 100 megabytes per second for the bulk reads. But what about for a short pre-handshake query? What's the limiting factor there? It's not the bulk read. It's the seek time. So there was another hint on the screen. There was a picture of an SSD, and it's all chips. They're really fast. Like they're very short latency. There's nothing moving around sluggishly. Right? We don't know how long the latency is, but we know it's going to be much shorter than a hard drive. Right? So it might be something. I don't know what a reasonable latency would be. I'd call it 10 microseconds, 100 microseconds, something like that. So orders of magnitude faster. So we can basically say there's no latency with SSDs. Now we can do an arbitrary number of short handshake requests with SSDs. Clearly, they're going to be more than 10 times faster. So it's better. Much better with SSDs. Almost everyone got that right. But what if we want to do lifetime yield queries? The limiting factor for the lifetime yield queries is bulk read throughput. This seek doesn't matter. We're seeking for 7 milliseconds, and then we're reading for a second. Right? So we just need to up our bulk read throughput. If we get 100 hard drives, that's going to be 10 times better than 10 SSDs because they have the same bulk read throughput each, right? Okay, so that'll be 10 times better with the hard drives. Finally, and this one was a little easier than I had first thought. So now instead of SSDs, we go with RAM. It's 10 times, costs 10 times as much per gigabyte, but we get 10 times the read speed. Okay, we're not saying which one is better anymore. We're saying how many lifetime yield queries could you handle if you stick it in your old server? Okay, so we have 10 times the read speed of the SSDs, which is 100 megabytes, now a gigabyte per second can read. Actually, that's similar to what we can do with the CPU as well. Right? We have only a gigahertz processor. So now this is going to start limiting us a little bit here too. We have to go through all these bytes. So we have basically we can compute, let's assume we can go through at the full gigabyte per second. That gives us 10 queries per, 10 of the long queries per second, whereas it used to be 1.
So 10 times more, right?
10 times more, yeah. But then what?
Well, obviously, the 10 times more queries, right? The question
Let's talk about it offline.
Okay.
Okay. So that's it. I need a glass of water. If you have little things like things you want to challenge, we'll just do it in the corridor to cool off. And for longer discussions, let's do it at office hours on Wednesday.